Welcome to another class on analysis of Boolean functions. In today's talk, we'll be continue to talk about hypercontractivity and some applications of it. Let me share my screen here. Okay. So just to recall you, we are focusing on this operator T-ho, which just which in the Fourier expansion of F acts as a multiplication. But this can also be seen, as we saw in the last class, the convolution against the kernel. In the kernel here, if I remember correctly, it should be just this guy here. Okay, where the convolution here is defined as the expectation of f of x, k of y, x, expectation in y. Okay, so we want to know the boundedness. So we want to know when such inequality holds with constant 1. We saw that if we put any constant, then it holds actually with constant 1. And when this holds independent of n, for every function, for every f, say from the Hamming cube, to either to k, where k can be either the complex numbers or the real numbers. So that's the question. That's the hypercontractivity question. Okay, that's what we want to know. And we made several observations in the last class. Let me just continue with a few. So let me define this. So I will say that P, Q, O is works. So we'll denote it like this. If we have this inequality, for every n and for every f, where if ρ is real, then we assume that k is real, and if ρ is complex, then we assume that k is complex. Okay. So we use this notation like this. So P, Q, and ρ, that means we have that. Okay. And we saw several conditions that ρ needs to satisfy. So we saw the most important ones that we saw, that if ρ is real, then ρ must be less or equal than root P minus 1 over Q minus 1. And if ρ is complex, then we saw that I think it was this, or maybe this was P minus 2 first. Let me just take a look, because I forgot exactly. Yes, that's it here. That's what we want. then we saw that these two conditions must be satisfied. And the goal is to show that these two conditions are enough. They are not only necessary, but they are sufficient. That's the goal of hypercontractivity. But let me continue to make some observations. Let me make another observation. Say observation 1 is that if we have P, Q, Ho, okay, if that works, then we have Q prime, P prime, Ho, R, and that also works, okay? And that's easy to show because if this is true, then it's easy to show that the adjoint satisfy the same. But then you have to inverse P prime less or equal than F Q prime, or I will denote here, for every exponent, P prime is the dual exponent of P. The formal definition is this, is the one that satisfies this equation, okay? And so you flip, you put the P prime here and you flip the P prime here. So basically what you're doing is the following. We have a map going T-Ho, going from say LP to LQ, and the adjoint goes then from the adjoint of the range space to the adjoint of the domain space, okay? And it has the same bound as the other guy, okay? This is easy, you can show this easily. But the thing is that what's the adjoint of T-Ho? And it's super easy to compute, you can even guess, it's just T-Ho R, okay? So that's why we have that implication. The second observation I want to make is for the case Ho real. So if PQ Ho works, then definitely PQ Ho prime works for all Ho prime immoduli less than the moduli of Ho. And why is that the case? Because it's easy actually, because suppose I want to show that this works. Now Ho prime just have a moduli less than the Ho. So then you can just write this as T Ho, and then T Ho prime divided by Ho F, using the group properties of this operator. And then you just bound this by T Ho prime over Ho F P. And now we saw by one of the observations of the previous class that this was true whenever this guy was real and had moduli less or equal than 1. And so, done. So therefore, to prove the hypercontractivity results, we want to prove the converse. We want to prove that this is not only necessary, but is also sufficient. So I only need to show this for Ho equals that number. Of course, by the same token here, well, it's easy to show that if it works for Ho, it works for minus Ho as well. And so therefore, we only need to show for this specific guy, okay, in the real case. Yes. Okay, and the other observation I would like to make is also pretty simple, also related with the case Ho is real. we saw that if rho is real, and then for this to work, okay, for this to work, we need a rho less or equal than this, but we definitely need rho less or equal than 1. We did make that observation as well. So if rho is less or equal than 1, real, and between -1 and 1, then we saw also that this is less than this. And that comes from writing this operator as an expectation, and you just move the moduli to the inside. Another way of seeing this is that if rho is between -1 and 1, then the moduli of this kernel, which is the moduli of this kernel, equals itself, because this thing here is always positive. And so if rho is between -1 and 1, k of rho is always greater or equal than 0. So you can always like put the moduli in the function f, and we can always prove when f is positive. So for rho real, we can always assume f is greater or equal than 0. Okay, and that would actually simplify things. Okay. So what I want to start now is start with a lemma, which due to Bonomi. Okay, so let's show this lemma. And the lemma of Bonomi is the following. Let pk be the projection that projects your function into functions of degree at most k. So pk projects to functions with degree less or equal than k. Then you ask, what is the norm of this projection k from as an operator from L2 to L4, and Bonomi gives the constant. Okay, and the proof is actually very nice. Is one of those cases where, to show that this is true in Hn, so this is for every f yeah, this would be real hypercontractivity. Say real. Okay. And so how do we prove that? And that's actually an illustration that we only need to show for n equals 1, and then we work through induction. And for n equals 1, so let's say for n equals 1, what's the function of degree less or equal than k? Well, for n equals 1, every function is just a plus bx1. And so if k is anything greater or equal than 1, it's just stating that so let's show that. So we're doing norm 4 here. So if k is greater or equal than 1, nothing changes about the function. And what is that? Okay, sorry, some technical problem. But then what is this? Let me raise this to the power 4. And this would be just expectation of this. And what is that? Well, this will end up being just a to the power 4, b to the power 4. And then you have like 6 times the square of this times the square of that. This will always also show up. And then we have the other bits, like with the cube of that times this and the cube of that times that. But this will always be 0 because when you do expectation, you will have always like an x1 multiplying the whole thing. And then it will be 0. So that would be exactly that. And this is definitely less than this, which is 3 times the expectation of f squared, say squared. And so then if we take in norms, then we conclude that take the 4th root, then you conclude that the norm of f is less or equal 4, norm 4 is less or equal to 3 to 1/4, norm of f2, which is definitely less than 3 to 1/2. That was if k was 1. So that was if k was greater or equal than 1, and if k is 0, that's trivial, because the left-hand side would be just a. This guy would be just that. Okay, so that's trivial. So let me do by induction. So assume by induction that the lemma is true for all k and say and n minus 1. Okay, all k in hn minus 1. Okay, that's the idea. And then in hj for j less or equal than, maybe hn minus 1 would be enough. Yes. So then how can I show for hn, that's the idea. But then you write f as some, say, f1 plus xn times f2, where f1 and f2 only depend on the first n minus 1 variables. And if you can actually give an explicit expression for f1, this is just the average operator en on f and f2. So this would be just average of f in the n variable, and the f2 would be just the derivative of f in the n variable, okay? And you can see the definitions of this in the first lecture. Fine, so we can always do that, and then okay, so then what is, oh, okay, so one thing we can always assume is that since we're dealing with projections, we can always assume that f itself has norm k. So the projection of it is just equal to itself, okay? So maybe we should write here. We can assume degree of f is less or equal than k. Because if it isn't, then this would be something of degree k, and this would be something that will have this first k part of f, and the remainder would just add something in here. And so if I can prove for every function of degree k, then I can definitely prove that. Okay, so I can assume that the operator doesn't do anything. So I just want to bound the L4 norm by the L2 norm for a function of degree at most k. And then you do the same trick. what's this guy? Okay, and yes, so this guy would be just, but the very same computation here does the job. And of course, that expectation of f squared is just f1 squared, the expectation of f1 squared plus the expectation of f2 squared. Okay, and then you use by induction that e of fj squared is less or equal. These guys have, and then you have to realize the degree of f1 will be less or equal than k, and then degree of f2 actually decreases because it's a derivative. It's k minus 1. Of course, because I multiply by xn, so the degree of f2 has to decrease. Okay, so what's the expectation of f4 of f1? Then you use induction. Induction, this would be just bounded by this thing, by induction. So we assume the result. That means that the expectation of, so if we raise this to the power 4, this would become 9k, and this would become just the expectation of f squared. So this is by induction. Then we have f2 squared to the power 4. Now f2 has a degree less, so it would be this. And then we have this, guys. So first we do Cauchy-Schwarz. And then we bound each one by the very same thing. So it would be 9, 1 to the k times 3 ef1 squared, ef2 squared. Oh, I think I'm missing a square here. Yes, I'm missing a square there. And so if you apply the same bound here, you would get what? 9k minus 1 and 9k minus 1, at least here, would go out, and there would be an extra 9 coming from this guy, which becomes a 3 after the root, and both of with the squares, now without the squares. Okay, and then if you just replace, then you conclude that f4 is just less or equal than what? 9k minus 1 expectation of f1 squared plus 9 expectation f2 squared plus 12 expectation f1 squared expectation of 2 squared. And so that's what you get. And then this is what? Less or equal. So what I do is just replace, put the 9 here. And is that, no, this is 18, sorry. Because it would be what? It would be 3 times 6. So it's 18. So if I put the 9 here, I increase, then I can factor that 9 and it comes out. This comes out. And this comes what? This becomes exactly 2 times 9. So this is definitely less or equal. And then that would be a square. And that is what? That is 9k e of f square, which is what we wanted to show, and that closes the induction. Okay, so again, easy to do, and this is one of these. So we presented before in the previous class an induction also on n, but now we use it in Minkowski inequality. So that we tensorized. So the idea was coming from tensorization, and here is not that not the same, is different. The idea is to remove a variable. But not thinking in terms that f was a tensor. Okay, and this induction works nicely when you have some even moments. When you don't have even moments, then there is no other alternative, and you have to use the tensorization method and Minkowski inequality. Okay, so as a corollary of this lemma, we have that if the degree of f is less or equal than k, then the probability of f minus its average being greater or equal than a half its variation, its standard deviation, say, is greater or equal than 9(1) minus k over 16. So you have an explicit bound for that deviation of your function. Okay. We put this in red. Okay, so let me go back to this proof. So how do we do that? Okay, so define G to be f minus the expectation of f divided by the square root of its variation. Okay, so now the expectation of G is 0, and the expectation of G squared is 1. Okay, and then you apply Bonomi's lemma. So which this is 4, this is k, this is just 9 to the k. And then what you have is that then you apply, so this next we use, it's called, I think it's Sigmoid inequality or something like that, but it's easy to prove, so let's prove it here. So I want to extract the information when the probability of, this looks weird. I want to know the probability that G is greater or equal than a half. So to extract that information, we use this trick here. Okay, and so in the first, there is no way around. You just use Cauchy-Schwarz, and then you have here probability that G is greater or equal than a half. And on the second, you just bound by a quarter times the probability of this, which you bound by 1. Okay, and so you get that 3/4 is less or equal, then let's raise to the square. So 9 over 16 is less or equal than EG to the 4, probability of G greater or equal than a half, but that's less or equal than 9k, probability that G is greater or equal than a half. And that finishes the proof. Okay. So this is it's sometimes called like the second moment method, which is if you want to bound, say so if you consider G squared as a function, and if you want to bound that expectation, what you do is you do this level set decomposition sum, and then in one part you apply some Holder inequality, and you have like the probability of G being large, and then the other part is just brutally bound by whatever you have. Hopefully you get something which is smaller in size than this, then you can get a bound for the probability of G being large, okay? And then you will bound this by bounding the second moment of G squared, okay? Okay, so another nice result is application is, so by the way, Bonomi's lemma, we will see in a moment, but Bonomi's lemma is actually a hidden hypercontractivity result. And we will show that in a moment. So indeed, we're actually giving application of hypercontractivity. Let me just give another one and then show why Bonomi's lemma is another hypercontractivity result. So that would be the FKN theorem, F due to Friedgut, Kalai, and Naor theorem, which is the following. If you sum f hat of I, you put a square, and that's greater or equal to 1 minus delta, and f is some, say, real function, then f is O of delta close to some function xi, plus or minus xi, okay? So there is some xi such that f is close to be just that guy. So just having the coefficients of order 1, oh, this has to be not for this. This function has to be Boolean, plus or minus 1. Yes. So we do know that the sum of all Fourier coefficients for all sets is 1. And if you're saying that the sum of just the Fourier coefficients of order 1 are pretty close to be 1 already, then it should mean that your function is just one of the xi's. And that's actually showing the case. Okay, so proof. Okay, how can we show that? Also recall that the distance between f and g is, for Boolean functions, is just this guy. So if g is some, let's say, plus or minus xi, the function xi, this would be what? 1 minus f hat plus or minus xi divided by 2. So we just need to show that the maxima of the moduli of the Fourier coefficient is greater or equal than some 1 minus O of delta. If that is true, then we bound the distance, okay? The distance also has an L2 representation, which if you figure it out, I think it would be the 1/4 of the L2 norm of f minus g. Okay, so then let L be the linear polynomial. I equals 1 to n, and note that L squared is what? Is 2 times, let me just write f hat of I as the Fourier transform as this guy. Okay, just too easy, the notation. Less than j, ij equals 1 to n, and this is xi xj plus the diagonal terms, which will be these guys. And we can assume, well, we're assuming that this is greater or equal than 1 over delta. Well, I can assume that this is exactly 1 minus delta without loss of generality. Okay, and but that would be 1 over delta, 1 minus delta actually squared, because oh no, that's just 1 minute. No. Okay. And so the whole point now is to compute this variation. That's the idea. And what is this variation? Well, we do know that this variation is the sum, well, of the Fourier coefficients S for S not empty. Okay, the square. But this guy only have this Fourier coefficients, okay? And so this would be exactly the square of the sum of the squares of this guy. So you get a 4, but with this a half here. So you just get a 2 I minus j fi fj hat square, which if we add and remove the diagonal, we get exactly sum of f hat I squared minus the square of the diagonal. Oh, sorry, minus the sum to the power 4. That would be the diagonal terms. And then what I could do, we can bound this from below by, well, first of all, this first bit is just 1 minus delta squared, and the other bit from below, I can bound because I can take the maxima of this fi squared, and then I will have the sum again with the squares, but the sum is always less or equal than 1, so I bound this by 1. Each one of these guys bigger or equal, less or equal than 1, so then I remove the square and just put the moduli. Okay. So we only need that the variation of L squared is like O of delta. If we have this, then we have our result. Okay, how can we show that? We apply the previous corollary. So this function L squared is not a function of order 2. So if I apply the previous corollary, what we get is like 9 times 144. Oh, not 9 times 16, sorry, which is 1 over 144, which says this is definitely greater than 10 to the minus 3. Okay, it's just bound by this to make it easier. But then what we do, what's the expectation of L squared? Well, we do have L squared right here. Is always the first Fourier coefficient, so is this guy. So this guy is exactly 1 minus delta. So this thing is less or equal than the probability of L squared minus 1 being greater or equal than. Okay, so let's assume now that the variation by contradiction is less or equal than some constant times delta. Okay, and so this thing is definitely what? Like some square root of c over 2 square root of delta minus delta. Okay, and then this is definitely less or equal if delta is small enough than some other constant c prime root delta. Okay, so fine, but note now that since f is just always plus or minus 1, And so this thing is saying that L squared minus 1 is greater or equal than 7. So this is saying that L is far from 1 and minus 1. And so then we can easily say that F minus L, because F is just plus or minus 1, has to be greater or equal than some other constant, square root of delta, when L squared minus 1 is greater or equal than C prime delta. Because, and I will leave this as an exercise for you to realize that this is true, but the point is that L squared minus 1 is bigger than something, which means that L is far from 1 and minus 1. And so if I test, in F is only plus or minus 1. So if I test F against L, this should be also bigger or equal than that number. Okay, so some other constant C prime, C2 primes. And so if that is true, then this thing, now using this information here, this thing is less or equal than the expectation of F minus L, say, divided by C2 primes root delta. Let me take that squared. Delta. Because in this set, this is always true. So if you divide and take the square, this bit is always greater or equal than 1. So this probability is less or equal than the probability when this is greater or equal than 1, which is the same as the x less or equal than the expectation of the indicator set, but then you can just multiply the less. In any case, it's easy to see that. Another way of seeing this by Markov's inequality, but in any case, you have that. Okay, but then what is this guy? So this C2 primes is squared. Let me write this as C3 primes delta, and then we have expectation of F minus L, which is the expectation of F squared minus expectation of L squared. Just because L is just like a projection of F under the space of functions which are linear. So you can deduce that this has to be true, or you can just open and do the calculation if you wish. But what is this? Well, let's see. What's the expectation of F squared? Well, F is Boolean, so this is always 1. And what is the expectation of L squared? This is the first Fourier coefficient of L squared, which is 1 minus delta. So you just get that divided by C3 primes delta. And that is just 1 divided by C3 primes. So then we conclude that C3 primes is less or equal than 10 to the power 3. Okay, so but then you can do something. So what's the dependence on C prime to C? Well, it's just, you can compute that exactly. It's just like 100 times C. And then what's the dependence of C2 primes to C prime? Well, it's just, again, like 100 times C prime. So then C2 primes is just like, it's just like 10 to the power 4 times C prime, times C at most. So since C3 prime is like, let me just be super generous, 10 to the 100, say, times C. Let's say C3 primes is like that, equal to that guy. So we can definitely take, let me see, C prime has to be something smaller. Okay, So, oh yeah, so it's like 10 to minus 100 times c. Because to go from here to here, maybe I have to reduce, and the c prime has to be small, and this c2 prime has to be even more small. So since times c, definitely, that would imply that, I know that c has to be less or equal than 10 to the power 300, I don't know, something like that. I'm being super generous. Of course, you can do these computations precisely, and you can know exactly what's the dependence of C3 primes in terms of C. And so this bound would imply a bound for C. Okay. However, I can take C to be anything and then redo the computation. So if I take C more than this bound, okay, then this computation would give you a contradiction. So we conclude that the variation of L squared is less or equal than some humongous C times delta. And that's what we wanted to show. Okay, and of course you can make this all precise, and you can actually give an estimate for the C here, and I will leave that as an exercise. But this is more or less the idea of the proof. Okay. So now let me give another theorem. And this will be the, say, what do I want to do here? Yeah, so let me give already the theorem. 2q is true for whole less or equal than 1 over q minus true and a whole real. And also p2 is true for whole less or equal than square root of p minus 1 and the whole real. Okay. So this will be the part of the hypercontractivity result that we want to prove, but in the case that one of these p's or q's are true. Okay, and this will be the bound we derived. Okay, and so we'll be showing that in part. Okay, and then in the next lecture we fully prove real hypercontractivity. Okay. Okay, so how can we actually show this? Okay, so let's prove that. And the proof is quite, it's actually quite simple. Let me do it. Okay, so first of all, by all the previous observations, I only need to show for n equals 1, and I only need to show this result. Because the other one is implied by this. And I can assume that rho is exactly root of p minus 1. Because I also made an observation, if I prove for this guy, then I prove for minus this guy. And if I prove for any, and then I can prove for any guy moduli less than, so that's the only case I have to do. Okay, so, but that translates into showing the following inequality. Oh, and also, if n is 1, before I write this, well, I can just factor the constant term, assume it's 1. So it will be just some guy of that form. And since I can assume that f is positive, that is, I can assume that b has moduli less or equal than 1, and then by continuity, I can just always assume that moduli of b is less than 1, okay, because I can assume that f is positive. And so that boils down to this inequality here. Okay. But this expectation is what? This is explicit, we can compute. And then this gets raised to p over 2. And then we just apply the fact that p is, oh, again, of course, I have to put here q greater or equal than 2, and here is p less or equal than 2, of course. And so since p minus 1 is less than 1, this is also less than 1. This is a number which is less than 1, and this is a number also which is less than 1. So this is less or equal than p over 2 p minus 1 b squared. Okay, so what we're using here is that 1 plus t to the theta is less or equal to 1 plus theta t if theta is less than 1 positive and t is greater or equal than 0. Okay, so the question is this true? Okay, but then what's this guy? Well, b, this guy is just this because this internal bit is positive and b is less or equal than 1. So I can just apply the binomial result, which is this is the expectation of the sum of b x1 to the m, and then p choose m. And again, the binomial result works whenever you have something here which is less than 1, and then you can put any real number positive here, and this summation will converge and have something nice. This summation will hold, that is, when if p is an integer, then for every m equals to that guy and bigger, this guy will be 0, okay? And so it will be exactly the binomial formula. And this is just the summation for m. Say, let me write the first term, which I want to isolate. And the odd moments here will die. So we just have m even. And then we just have that. Okay, so now the question is p over 2 p minus 1 less or equal than the very first term in here, which also has a b squared, which is p choose 2. And the question is that yes, exactly, because it's equal to that. And then the proof is finished. Okay. And so we do have hypercontractivity for those cases. And let me write some applications here. I will not prove them. I will just mention where they are. They are in chapter 9 of the book, and you can check it out. So one application, and these are all simple to show. So what application is to assume the degree of your function f is less or equal than k, and then f is some real function. Then you know that so you can also always think, well, if I have a function and you have to compute the L2 norm or the LQ norm, how do I lose if I try to bound that by the L2 norm? And the answer is, well, if you don't go in the right direction, you can always, you lose at most to some constant c raised to the degree of your function. This is sort of a nice thing to know. And this is an application of this result we just showed. So we'll leave it as an exercise, it's easy to show. Another nice application is the following. So So that is going like in the opposite direction. So suppose I have some norm Q, so norm Q which is bigger than 2, then I can bound from above. From these two, if I have a norm P, yeah, so the norms are increasing with Q. So we do know that this guy is bigger or equal than 2. And then we're saying that it's less or equal than this. So it's equivalent to the norm 2, and the norm loses by some constant raised to the power, to the degree of the function. And the same thing here, P is less than 2. So we do know that this guy here is less or equal than the norm 2. And so we're saying that the norm 2 is comparable again with the norm P if P is less than 2. But again, you lose something like a power. So the bottom line, this is saying that P norm 2 is comparable with any other norm, say norm R. And the actual constant here is just some C raised to the degree of F. Okay. This is what these two lemmas say. And these are, again, applications of hypercontractivity. So maybe I can say, just to give a hint, what's the trick here? Well, the trick here is to write F as T Q minus 1, T 1 over Q minus 1 times F, and apply hypercontractivity. And the trick here is to write F squared as some F 2 minus theta P, and then some F, say theta P, model I say. And where this theta is just some number less than 1, bigger than 0. And then you want to send theta to 0. And then what you do here is you apply holder in this function. So to get, so holder would be with the exponent 1 over theta. So to get a norm P from this guy, and whatever you get on here, you apply hypercontractivity. So you recover some norm P, and then in the end, you will have something like, F2 is less or equal than Fp, some constant of theta raised to the power k, where k is the degree of the function. And then when you say theta to 0, this constant theta will converge to this guy here. That's the idea. Some other application. So this is not honestly. So you know that if you have a function of a certain degree, so if the degree is something like, it has a certain like exponential decay with a polynomial here, and the higher the degree, the slower is the decay. So, and this again is an application of hypercontractivity. Maybe using those, the corollary I presented before as well, when you have something like that. And so I guess this is theorem 9.23. I don't recall the other ones. And then another nice application to think is 9.24 is this one, that the probability of F being greater than the expectation of F is greater or equal than 1/4 e to the minus 2k. And we have other bunch of applications that we will explore in the next lecture. And we also try to prove a full real hypercontractivity result in the next lecture. So I see you next time.